For our second video in our fluids unit, we're going to talk about the idea of pressure. And again, please make sure you take notes, and if it asks you to pause it and think about something, make sure you pause it and think about something. So let's start by kind of thinking about two situations and how they might be different or the same. So one situation is you're standing in a room and someone walks by and steps on you with a high heel. So this is a high heel. It's just it's a high heel. It's actually called a stiletto high heel, where it has a really, really small point on the end of the heel. So that's situation one. Situation two is, let's take a look at a video.
Describe what we're about to accomplish.
All right, Dan's birthday. We were talking about the weight of trucks and cars and so forth, and came up about running over somebody's foot. Dan and Monica have both said that they've had their foot run over and it doesn't hurt. So here I am, the driver, Paul Bird, ready to run over some foot.
Yeah, I'm ready.
All right, let's do it.
Born ready to get my foot run over by a truck.
Yeah. All right.
Yeah, floor it.
Let's do it.
Ready?
Ready. Filming.
I got my safety goggles on. Ready? Ready?
Yeah.
All right, first thing I just want to say, do not do either of these things at home. I've had both done to me and they can hurt. So please do not do it unless you're a trained person with a shaved head wearing wraparound sunglasses in a pickup truck. So now think, which one's going to hurt more? Getting stepped on by a high heel or getting your foot run over by a truck? Again, take a few seconds to jot your answer down.
Look. Easy.
Wait, I don't think I'm good. Okay. Did you move?
Ready?
Yeah,
All right,
fast.
go.
Perfect. Oh, that was easy. That's nothing. Fast.
Go.
Perfect.
And that's situation two. So it looks like that it doesn't really hurt too much to get your foot run over by a car. But it does hurt. I can tell you again from experience, it does hurt a lot getting your foot stepped on by someone in stiletto heels. And I also can let you know, I've had both of them happen to me, and getting your foot run over doesn't really hurt. Now you gotta be a little bit careful. If it just grazes the edge, it can pinch you, and that could hurt a lot. But as long as it runs over your foot like it was in this video, it shouldn't hurt you. But again, do not try these things at home. So the question is though, why? It seems like just a person stepping on you versus a truck running over you, the truck should hurt a lot more, but it doesn't. So to try to figure this out, we're gonna have to define a new term, something called pressure. Where pressure, let's just say in a simple sense, it's just how a force is distributed. So in a mathematical sense, we can say that the pressure is just the force per area. So the force applied to something divided by the area that it is distributed across. So we can say that P is F over A. And if we look at what units we might use, any unit of force and any unit of area will work. So we're going to use newtons per square meter in the metric system, which is also sometimes called a Pascal. In America, you might use something called pounds per square inch, which you might know as a PSI. Like it's probably written on your bike tires or car tires. People sometimes use something called an ATM. We'll see later on why we use that. And because a Pascal is pretty small, a Newton is a really small force, and a meter squared is a really big area. So a Pascal is pretty small. They'll often use kilopascals, which is just 1,000 pascals or 1,000 newtons per square meter of pressure. So let's go back to our two situations, see if we can figure out why one of them was kind of a little more dangerous than the other one, but kind of not what we expected, that the one with the smaller force seemed to be more dangerous. So let's look at our cases. So if we want to use the idea of pressure, we want to find the force applied in each case, and we want to find the area in each case. So let's look at, let's see. So in each case where we have no acceleration, if we draw a free body diagram, we're going to have, let's see, your foot in both cases is going to kind of be applying some upward normal force on something, and something's going to be pushing on it. But again, I'm not going to spend a lot of time, but really the force applied to the foot is going to equal the weight of the thing on top of it, because your foot's acting like the ground is applying a normal force on the tire and on the heel, and then that tire and heel is applying a normal force back, and then because there's no acceleration, that normal force happens to be equal to the weight of the thing on top of you. Now, if they were stamping your foot or the car was dropping your foot, that could be bigger. But let's say in our case, it's the safest case where they're just standing, not moving on top of you. So we can say the force is going to be just the weight of the object, and the area is going to be the area it's distributed over. So let's make an assumption for the person. Let's say their mass is about 60 kilograms. For the car, I'll use my car's mass. It's about 1,500 kilograms. So the weight of the person is going to be, let's see, 60 kilograms. Let's use 10 for our gravity constant, just to make life a little bit easier. So that's 600 newtons of force. Now the person has 2 feet. It looks like their other foot is actually on the ground. So we're going to say the weight per foot that's being applied right here is actually going to be half of that. So our weight per foot is going to be, or our force is going to be 300 newtons. For our car, the weight of our car is going to be 1,500 kilograms times our same gravity constant. So that's 15,000 newtons. And again, a car has 4 tires. They all seem to be on the ground here. So the weight per tire is going to be a quarter of that, which is about, I think, 3,750. 3,750 newtons. So that's our force in this case. Now let's see our area for the heel. That's pretty small. Let's say it's about ½ inch square. So that's about 1.27 centimeters square, which is about 1.6 square centimeters, which is about 0.000, I think. Yeah, 3 zeros, 16 square meters. And for our car tire, let's say the area here, it's going to be about, I don't know, let's make an assumption. So it's kind of this area down here, not the area of your foot, but the area of the car tire that's kind of in contact with your foot in the ground. Let's say it's about 8 inches square. So that's about going to be, I don't know, about 20 centimeters square, just to make numbers easy. So that's 400 square centimeters, which is about 0.04 square meters. Now, if we find the pressure in each case, the pressure for the heel is going to be 300 newtons divided by 0.00016 square meters. And that's going to give you around a little less than 2 million, I think. So about 1.87 million newtons per meter squared. For our car tire, we're going to get, let's see, our force of 3,750 over our 0.04, and that's going to give us around a little less than 100,000. And if we compare these, this is actually, in the case of the heel, it's actually 20 times greater than the car tires. Even though the car weighs a lot more than a person, a 60 kilogram person on Earth, the pressure, because this area is so small, the pressure is a lot greater. So in this case, our high heel is going to hurt a lot more than getting your foot run over by a car, mainly because that area is so tiny. So even a small force can apply huge pressure and can do damage to your foot. Next thing is, okay, great, that's just an idea of what pressure is, but we're more concerned about pressure in fluids. So how can fluids apply a pressure when they kind of move around and reform to fit whatever container they're in? So if we look at a situation here, we have a container. I'm going to pump in some gas into it. And if you look, when the gas molecules are inside this container and they're bouncing around, they keep smashing against, or they collide with the edges of this container. And every time they collide with the edge of a container, there's a little tiny force applied as the gas particle gets kind of reflected back. There's an impulse applied on it. That means the particle applies an impulse to the container, and the container feels these bunch of forces. If you kind of take the total effect of all the collisions we get kind of this kind of fluid pressure. So this fluid can apply a force averaged over an area due to all these little tiny collisions summed up of all the particles in the fluid. Now let's go one step further. So we have a fluid here, let's say it's a liquid or fluid, and it's inside this container, and there is a cylinder on, or it's a kind of cylindrical, but there is a piston on the end of each side. It's called side A and side B. And if I apply a small force over here, or a force at force A, what's going to be felt at B? So again, just take 10 seconds, take a quick think. I apply force at A, what's B going to feel? Well, one of our rules of fluids is that, what's called Pascal's principle, is that the pressure is constant. As long as your height doesn't change too much throughout a fluid. So if our pressure is constant, that means the pressure at A has got to equal the pressure at B. Now, I apply a force at A. Well, the area at A is actually small compared to the area at B. So if I know the pressure at A equals the pressure at B, but the area at A is less than the area at B, that means for the pressure, since we know pressure now is force per area, if one has a smaller area, that means that one also must have a, if this is small, this has got to be small to make the pressure stay constant. So that means the force at A is going to be also less than the force at B. So we get what we get kind of a mechanical advantage. We get a force multiplier. We apply a force at A and we get a bigger force over here at B because the areas are different. And that's mainly because the pressure is constant throughout our fluid. Again, this is known as Pascal's principle. It's used in hydraulics. For example, the brakes in your car, you push in your brake pedal. There's a little tube inside there. You push a fluid inside there, your brake fluid. And that pressure that you apply stays constant throughout the entire thing. But the other end, where you have calipers, they have a bigger area. And so you can apply a small force to your brake pedal, and you get a big force applied to your brakes, and you can actually stop your car with a nice, easy push of your foot. Okay, great. This seems like it's magic, though. We get a force multiplier, but we got to give up something. There's got to be a trade-off. So what's the trade-off? Well, again, if we say pressure is constant, we know force per area is constant. But if I were to move this piston, let's say I move this piston some distance delta x, and we still have our area A over here. And so this piston moves down to here. Now the volume that it moved, that kind of is shifted over here, is going to be the area of A times how far it moved. Now, if I move so much fluid, if I move all this fluid into here somewhere, I got to move all the fluid over here as well. So when this thing moves some delta xb over here, and it has its area, that change in volume over here at point A is got to be the same as a change in volume at point B. And you might be able to kind of see our trade-off now that the volume at B is going to be the same as the volume at A, and this one's going to be the area at B times how far it moves at B. So you can kind of see that since the area at A is smaller than the area at B, that means the movement at A has to be greater than the movement at B. So to get some motion at B, you need a lot more motion at A. So there's our trade-off, that yes, you get to multiply your force, but the trade-off is you need if you want to move something, you need a bigger distance. And what really is happening is that the work at A is the same as the work done at B. The work is staying constant. We don't get free work out of the deal. So yeah, we get a multiplied force, but we got to move things farther. It even works with lifts. Again, if the height changes, it's a little bit different. We have to use something else. We'll learn a little bit later. But in this case, we can have some object that has a small force over a small area, and that can balance out a big force, or a big weight in this case, if it's applied over a bigger area. So in summary, we get the idea that pressure is force per area, that pressure remains constant throughout a fluid, so that force per area remains constant throughout a fluid.